Hello again. This is Math 2245 coming to you from the College of DuPage. The title of this lecture is Spatial Matrices. As always, please be an attentive learner while watching this video. Here we talk about some special matrices, and we're going to need these later as we prove some things, so we'll get their definitions and some fundamental properties out of the way. The first that we're going to look at here is called a diagonal matrix. And a diagonal matrix has the form of, you have numbers down the diagonal and zeros off that diagonal. And the numbers on the diagonal could, in fact, have zeros amongst these di's, but we know that there's zeros above and zero below, and so this is called a diagonal matrix. The main diagonal potentially has non-zero entries. Any entry off the main diagonal must be zero, and note it's possible to have more than one of the main diagonal entries to be zero as well and still be a diagonal matrix. And in fact, we've encountered diagonal matrices before. In fact, the identity matrix is a diagonal matrix. So here's a theorem. Suppose that D is a diagonal matrix and D1 through Dn are the entries on the main diagonal. If one or more of the di's are zero, then the matrix is singular. That means there is no inverse. If, on the other hand, none of the di's are zero, then the matrix is invertible, and the inverse is 1 over D1, 1 over D2, 1 over D3, all the way down to 1 over Dn, and zeros off that. Let's look at the proof of this. First, recall that if D is row equivalent to the identity matrix, then D is invertible. And if D is not row equivalent to the identity matrix, then D is singular. Now, if none of the di's on the diagonal are zero, then we can reduce this capital D to the identity simply by dividing each of the rows in its diagonal entry, which we can do since we've assumed none of them are zero. And so in this case, the capital D matrix will be row equivalent to the identity matrix and hence invertible. Therefore, in this case, it's invertible. And we'll leave it to you to verify that the inverse is what it claims to be, but that's simply just matrix multiplication, and you compute it and you will get this. Now, suppose that at least one of them, the di's, is zero. In this case, we will have a row of all zeros. And because D is a diagonal matrix, all the entries above the main diagonal in this row will also be zero. And so there is no way for us to use elementary row operations to put a 1 into the main diagonal. And so in this case, D will not ever be row equivalent to the identity matrix and hence must be singular. Please think through this argument. Powers of diagonal matrices are also easy to compute because if D is a diagonal matrix and K is any integer, any positive integer, well actually it is positive or negative as long as the diagonal elements aren't zero, then D raised to the K power is this. The next kind of matrix we're going to talk about is called triangular matrices. And there are two kinds of triangular matrix. For an upper triangular matrix, the matrix must be square and all the entries below the main diagonal are zero. Not the main diagonal itself, but below the main diagonal. And the main diagonal entries and the entries above it may or may not be zero. That is for upper triangular. A lower triangular matrix is just the opposite. The matrix is still a square matrix, and all the entries of the lower triangular matrix above the main diagonal are zero, and the main diagonal entries and those below it may or may not be zero. So here is what that would look like. So here is an upper triangular matrix. You can see that the main diagonal and everything above it might be non-zero, but anything below is zero. That's upper triangular. Similarly, lower triangular has the main diagonal, and anything below the main diagonal could be non-zero, but everything above the main diagonal is zero. So the uij's and lij's may or may not be zero. And sometimes if we don't care if the matrix is upper or lower triangular, we might just call it a triangular matrix. And note that, given the definition, a diagonal matrix can be thought of as both an upper triangular matrix and a lower triangular matrix. So here's a theorem describing how invertibility works for triangular matrices. So the theorem states, if A is a triangular matrix with main diagonal A1, 1, A2, 2, all the way down to A in M, in N, then if one or more of the AII's are zero, the matrix is singular. On the other hand, if AII does not equal zero for all I, then the matrix is invertible. Let's look at how the proof of this will work. First, assume that none of these diagonal elements are zero. In this case, we can divide each row by AII since it's not zero, and that'll put a 1 in the main diagonal for each row. And now use the third row operation to eliminate all the non-zero entries above the main diagonal entry for an upper triangular, or below it for a lower triangular matrix. When done with these operations, we have reduced A to the identity matrix, and therefore its row equivalent to identity, and so must be invertible. Now let's assume that at least one of these AII's are zero. In this case, we can't get a 1 in the main diagonal just by dividing by this as we did in the first place. Now suppose that we have an upper triangular matrix, and a similar argument would work for a lower triangular matrix. In this case, we could use the third row operation using one of the rows above this to get a 1 in the main diagonal entry. However, this will put non-zero if we do not care if the matrix is upper or lower triangular, we will generally just call it triangular. Note as well that a diagonal matrix can be thought of as both if we do not care if the matrix is upper or lower triangular, we will generally just call it triangular. And you should note that a diagonal matrix, by the definition, can be thought of as both an upper triangular matrix and a lower triangular matrix. So here's a theorem about the invertibility of triangular matrices. And the theorem states, if capital A is a triangular matrix with main diagonal entries, lowercase a11, lowercase a22, all the way through lowercase a in n, then if one or more of the AII's are zero, then the matrix will be singular. On the other hand, if they are none are zero, the AII's are not equal to zero for all I, then the matrix is invertible. Here's an outline of the proof. First of all, if the AII's are not equal to zero for all I's, then we can divide each row by AII since it's not zero. That puts a 1 on the main diagonal in each row. Now we can use a third row operation to eliminate all the non-zero entries above the main diagonal entry for an upper triangular matrix, or below it for a lower triangular matrix. And when we're done with these operations, we've reduced capital A to the identity matrix. Therefore, it is row equivalent to the identity, and so must be invertible by a previous theorem. Now assume that at least one of these is zero. In this case, we can't get a 1 in the main diagonal by dividing, as we did in the first place. And now For a second, let's suppose we have an upper triangular matrix. In this case, we could use a third row operation using one of the rows above it to get a 1 in the main diagonal. However, this will also put non-zero entries to the left of this as well. In other words, we're not going to be able to reduce A to the identity matrix. The same type of problem will arise if we've got a lower triangular matrix. In this case, capital A will not be row equivalent to the identity and hence will be singular. Some more theorems about triangular matrices, and we're not going to prove these, but we are going to state them, and you should think about how you would prove them. We will do some examples of these later, however, just to see how this will work. So the product of lower triangular matrices will also be lower triangular. Similarly, the product of upper triangular matrices will be upper triangular. And the inverse of an invertible lower triangular matrix will be lower triangular, and the inverse of an invertible upper triangular matrix will also be upper triangular. And the proof follows from how products and inverses are found, and this is left to you. Now we're also going to talk about something we have spoken about before, but it fits in nicely here, and that's the idea of a symmetric matrix. And let's review the definition again. So suppose you have an N by M matrix. A is called symmetric if A is equal to A transpose. Now notice that for a matrix to be symmetric, it has to be square because the size of the transpose and the matrix itself have to be exactly the same. So a symmetric matrix must be N by N. It must be square. So just to look at some examples then of matrices that are going to be equal to transpose. Here we have it, and you can see that you've got 6 and 6 here. Here on the diagonals you have minus 10, minus 10. Here you have 3, 3. Here you have 1, 0, 1, 0, and here you have minus 4, minus 4, and here you have 8 and 8, and here's 10. Also, so all of these are symmetric, and you can do that by taking the transpose and seeing that you get exactly the same thing. And again, looking at the diagonals off the main diagonal help you realize the symmetry that exists across the main diagonal. And here are some facts about the arithmetic that we can do with symmetric matrices. If you have two symmetric matrices of the same size, and if lowercase c is any scalar, then you can add two symmetric matrices of the same size and get a symmetric matrix. C times A would be symmetric, and if A is symmetric, then the transpose of A is also symmetric. Note that the product of two symmetric matrices might not be symmetric. In fact, probably is not symmetric. To see why, consider the following. Suppose both A and B are symmetric matrices of the same size. Then the transpose of AB is B transpose A transpose, but that's BA. So you see the transpose of AB is BA, and so that means that in order for this to be true, that's only true if A and B commute. If A and B do commute, then the product will be symmetric. Now, if A is any N by M matrix, then because A transpose will have M by N, both A transpose, and A transpose A will be defined. And in fact, will be square matrices. And A times A transpose has size N in this case, and A transpose A has size M times M. So here are a couple of quick facts about symmetric matrices. Both A transpose, and A transpose A are symmetric. This is for any matrix A. If A is an invertible symmetric matrix, then the inverse is going to be symmetric. And if A is invertible, then A transpose, and A transpose A are both invertible as well. Let's look at the proof of this significant theorem. Okay, so what we'll do in part A is we'll take a general A, and we'll show that A transpose is symmetric, and leave you the other for you to verify the other way. So to show that A transpose is symmetric, we need to show that the transpose of this matrix is the same as the original matrix. This is quite simple because transpose, the transpose of it, is going to be the transpose in the reverse order. But the transpose of the transpose is the matrix itself. And so we get the transpose is equal to the matrix itself, which is the definition of symmetric. Now here we need a theorem from a previous section to show that the inverse of the transpose is the inverse. And here's the work. So A inverse transpose is equal to A transpose inverse. But A transpose is the same as A because it's symmetric, and therefore the inverse of the transpose of the inverse is the function itself. So that means that A inverse is symmetric because A inverse transpose is the same as A inverse. Finally, if A is invertible, then we know that A transpose, is invertible. And since the product of invertible matrices is invertible, both A transpose, and A transpose A are invertible. Okay, so now what we're going to do is, and this is the theorem we didn't prove, but we're going to do some calculations and just see what happens. So we'll start with A, B, and both A and B are upper. Let's see, both A and B are upper triangular. We'll have a matrix C here, and C is this general matrix, and D is a 4 by 3, and E, and notice that E is symmetric. Anyway, let's compute a few of these. So this is A times B. So we're multiplying two upper triangular matrices. So let's just do it, and you should follow this calculation. But what we're going to see is let's go back and do that. So what we see is that the product of two upper triangular matrices was upper triangular. Here we're going to find C inverse. So here is C. We go through using these row operations to find the inverse. And you see this was a lower triangular matrix, and the inverse is also lower triangular. Here we're having D transpose times D, and when we do that calculation, you see we get a symmetric matrix: 16, 16, 15, 15, 2 minus 4, 2 minus 4, minus 2 minus 2, and minus 11 and minus 11. So, as suggested by the theorem, this product is symmetric, even though D itself was not symmetric, or square even, for that matter. And finally, here's the work for E inverse. So we're going to find E inverse. So we start with E, and we do the work with the row operations to get finally the inverse. We get the identity matrix here, meaning this has to be the inverse. So E inverse is also symmetric. You see here's the main diagonal, or 0, 0, 2, 2, and 1, 1. So the inverse of a symmetric matrix is also symmetric. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself, because self-care is important, and of each other. We're all in this together. May God bless you all.